All right. Next, we have group 6 looking at millimeter properties and what you can learn.
Okay. Hi, everyone. We're group 6. We were supervised by Jerome and Antoine, and we were looking at estimating the H2 column density using combined molecular lines in the Orion B cloud. So just to start, when we look at giant molecular clouds, generally we're looking at investigating star formation. And we look at these dense cores, which are where stars are formed, and those generally have lower temperatures. And because of that lower temperature, it's harder to directly observe H2. So we need to look at other quantities, such as dust and molecular lines. So first of all, with dust, it has the advantage of being optically thin. However, it lacks the velocity information, and we would need measurements in the far infrared. On the other hand, with rotational lines, we do have that velocity information, and using ground-based observing, we can get a very high angular resolution. So generally using the XCO relationship between the emission of CO and the amount of H2, it's generally assumed to be a linear relationship. But when we look at our data there on the right, you see that that relationship fails. So if you can see in red, that's an assumed linear relationship. And in green, that's the best fit of line for our data. So isn't quite the best assumption for our data. So the main question driving our project was, can we go beyond this XCO assumption and estimate this H2 column density using more lines and machine learning techniques? And a quick look at our data. So we used data from the IRAM 30-meter telescope. We had 12 different species that we were looking at. These are the integrated intensity maps. And we had several isotopologues. For example, on the top row, we have 12CO, 13CO, C18O, and so on. And we also had our column density. So we started by visually analyzing these maps before moving on to other techniques.
Okay. By comparing the integrated intensity with the extinctions, we found that not only the CO line, but also the other molecular lines have a correlation with the extinction, which represent the column density of the hydrogen molecule. So before we find a direct connection from the molecular lines to the column density, we wanted to explore if different lines correlate to each other and if the combination of these lines has a connection to the column density. So we did so to do so, we performed the principal component analysis on the data of our whole 12 line data. So this PCA method is useful to find the linear correlations existing in the data, especially useful in the case when the data has high dimension, like our case that have 12 lines. And PCA find the intrinsic characteristics that describe the data. So we call these characteristics as the principal component. And it also tells us which component is more influential and which component is the least influential. The left figure shows the influence of each principal component. We can see the first component makes about 60% variance of the whole distribution, which means that it's the most influential component. And we check the contribution of each line on this first component, the PC1. In the right panel, we can see that all 12 lines somehow contribute to the PC1 in the positive way and in a quite similar amount. So next, we compare the 2D distribution of the PC1 with the 2D map of the column density. Here we can directly see that the PC1 somehow traces the column density information, which means that all the 12 line intensities are related to the column density. But when we directly compare the column density versus the PC1 values, we can see the increasing trend, but it's not the perfect linear. So this means that we need a nonlinear function to link the line intensities and the column density of the hydrogen molecule.
So what do we know so far? We know that we have all these lines, emission lines, all of these intensities are related to the column density of H2. And we know that we want to find a direct link between the column densities of H2 and the intensity of the lines we have. So let us have a look at this problem. This is how we can represent it. We have this huge data set, and we want to map the column densities. And we want to use fancy machine learning to do it. Let's look at it a bit more technically. You have this plot, which you already saw like 3 times. And this is the integrated density. This is the dust dust extinction, which is standing in for the column density of H2. And you already know that this line fit is not enough. This is a nonlinear plot. So we cannot have a simple nonlinear function. What if I took a chunk out of this map, this plot, and asked you to predict how, based on these other points, what this point distribution should be here? So to do that, we have, again, fancy machine learning, and we decided to use a decision tree. So how does a decision tree work? Let's learn with cute animals. So if we plot these cute animals on a plot like this, how would you separate the cute animals? You would probably think, oh, maybe there's a color yellow that separates them, there's a height that separates them, etc., etc. And based on these different attributes, you separate out all the points. And now you have smaller groupings of points that you can fit more non-linearly and more accurately to this plot. So the model that we have learns this distribution based on the training data we give it, and it maps out the column density. But wait, this is a big data set. There is a problem of overfitting, other problems. So what we use is instead a random forest, which is a collection of these decision trees. And once we have a bunch of results from the decision trees, we average them out and we get a random forest. Why random? Because it takes out random samplings of input points rather than all the points at the same time. And so it is great for nonlinear data. And we don't need to normalize it or remove blank points or like do some great pre-processing or anything. But we still need to prepare it a little bit just between the training and the test data. And here you see a representation of it. This is not how we actually divided it. This is just a representation. So you see this grid map, and this little section of the map is something we use as a validation set. This is an area of the Horsehead Nebula. So it has more physical features, like it's PDR. It has more density. It has more noise. So we use the rest of the map as a training set and train our model and try to predict what the column densities should be here. We already know the column densities here, so we can also compare it with the ground truth. And yeah, for the next step, I will hand over so that you can see the results.
Yeah, so the last thing that we need to do is validate our results, or actually show them. Let me see. Okay. Yeah, so it needs to be said that our function was trained only on this chunk without the Horsehead Nebula. And now we're going to use it to recreate a picture of the Horsehead Nebula. You know this? This is, yeah. So what you see here is the H2 column density observed. So with observing dust extinction and mapping it to H2 column density, then the predicted one and the difference. For the linear method that has been used widely, XCO, and in the bottom, our non-linear method, our new method. So you see that given the data in these wonderful green squares or rectangles, the previously known method, the linear method, tends to fail by predicting these dense cores, which you see they're basically not here, which is due to the fact that CO saturates at some point, so we can't get any information out of that. And you see that the difference map has a large spread in difference in log space. However, our method is successful in recreating these dense cores. We still have some problems with difference, but the spread in difference is way smaller than the previously known method. So at least for the Horsehead Nebula, our method is actually superior. And what comes now is the conclusion.
So to summarize, what did we actually do? We investigated the relation between molecular lines and the column density of hydrogen. We used PCA for that to find correlation between lines. Then we used random forest to link those lines to column density of hydrogen. So then what did we find? We find that our method works better than XCO, at least at our data. And then what will we do? We can improve our method. We can find new data and try our methods on these data. And if it's successful, we can try to predict new data. Okay, yeah, and that's all.
Millimeter crowd. We've got several.
I was wondering about this horse nebula because in this purple picture on the left, it looked like your predicted H2 was actually following some features that were visible in this purple picture. So do you know what this purple picture is? And there was some outflow feature or something. It looked like this, some cone. And so do you know what this is? And do you know why it's not visible in the observed H2? Like this thing that is going down. It's visible on the left picture and also on your predicted in the lower right. I think it looks a bit like this, no?
Yeah. Well, we have to look at that actually. Interesting. I mean, there's definitely something here. We see it here, but we don't see it because of the movement. I'll see it. It's predicted.
Oh, you're near me. Okay. We definitely predicted here as well, but yeah. Jerome, do you have an explanation for that? No? Okay.
I was wondering if you're able to tell in your in the model you used to predict if there were certain lines that were most important in addition to CO, or maybe CO wasn't important at all. I don't know.
Yeah. So this figure, yeah, the red panel shows the, how can I say, importance of each emission lines on the column density. So we can see, of course, the CO lines is important, but that's all the same to the other molecules. Yeah, they contribute somewhat similarly.
Right, one further question while group 8 comes down.
So this looks really cool and the prediction is very exciting. And I think you said that in the literature, typically people are just using a linear correlation to predict the masses. So I'm wondering, like, could you now run with this and apply it all over the place, or have people already started to do that? Or yeah, I guess, like, how excited should I be about the PCA approach?
How excited are you? I mean, yes, there is. You actually using machine learning, right? Yeah. I mean, there are. You can always use many different kind of models and apply it to different data sets and see how the result is. But I think there is still the problem that we have to constrain the results to be physical, right? And there are a lot of approaches that many people are trying in literature, but in my view, that's still the problem we have. So just be careful.
It's also pretty hard if you think that you need 12 lines before, like observations of 12 lines in velocity space, and then you can make predictions. So maybe a new step would be to narrow it down to like 6 or 7 of the most important lines. Yeah.
But PCA and machine learning are really effective when you're trying to denoise your data. If you're interested, contact me.
Let's thank the Millimeter group again. Thank you.